So, welcome everyone to the 11th lecture on statistical theory for deep learning. Last time we have seen the proof of theorem 3.1, which provides us with an opportunity to bound the difference between a sample mean and an expectation uniformly over a function space. More precisely, we let z, z1 to zn be IID, RD value general variables. We let b be a number greater 0. We let calligraphic g be a set of functions, a small g from RD in the interval from 0 to b. Then for every n and every epsilon, we have the following bound: the probability that the supremum over all g and calligraphic g of the absolute value of 1 divided by n times sum I equal 1 to n g of zi, so the sample mean of the g of z1 to zn minus the expectation, the corresponding expectation, the expectation of g of z. Probability that this supremum over this g in calligraphic c of this absolute value escaped in epsilon is less than 8 times the expectation of the covering number, L1 covering number of g on z1n. Z1n are the z1 to zn. With radius epsilon divided by 8 times e with power minus n epsilon squared divided by 128 times b squared. We can use this theorem to bound the L2 error of the least squares estimate. Let me explain this. So we have IID random variables xy, x1, y1, x2, y2, and so on. We want to estimate the regression function m of x, which is the corresponding conditional expectation of y given capital X equal to small x by some function of our data. Data is x1, y1 up to xn, yn. We can use the least square estimate, where we just choose the function which minimizes the empirical L2 risk. So 1 over n times sum I equal 1 to n f of xi minus y squared over some function space which I call calligraphic fn. Then we look at its L2 error. We know from the motivation of the chapter, which I've given in the lecture 1 week before, that this is just the L2 risk of the estimate minus the L2 risk of the regression function. I write this as the L2 risk of the estimate. Here are my data x1, y1 up to xn, yn, and I subtract first the empirical L2 risk. Then I add again the empirical L2 risk. So that just cancelled out, and now I have to subtract the L2 risk of the regression function. And I use these two terms and consider them separately. This is my error decomposition. In the first term I call T1n, the second term I call T2n. Then we know that this guy here is the minimum over the function space, so you can upper bound it by the minimum of the empirical L2 risk of some function f in fn, and then you compute its expectation, and the expectation of the minimum is less than the minimum of the expectation, and then you have the L2 risk of your function minus the L2 is of the regression function, which gives you again the L2 error. So you see immediately that the expectation of the 2n is now s. It's less than the minimum over f and fn. I write minimum, it could be also an infimum. Not important. F of x minus f of x. Dx. And that's the so-called approximation error that measures how well you can approximate your unknown regression function by the function from your function space. And this error comes from the fact that you restrict your estimate to be a function from this function space, so it cannot approximate the regression function better than the best function in this one. So you cannot avoid this kind of error. Then you can look at the first term. And here I look at the probability that this one is greater than some t, so I make some bound in probability. Maybe look at some conversion probability to get some idea. And now I can replace this one by, well, the function, the estimate ml is in, but the estimate ml is one of my functions from my function space, so I can upper bound this by the supremum over all f and fn over these guys here. So that's less than. And then I don't write f of x minus y squared, I use the new function g, and the new function space gn. And then we have here and I add some absolute value. Squared. And I have to define what z is. Z is just the xy. Zi is then correspondingly xy, xi, yi. And I also have to define what g is. What gn. Now I make all functions from Rd times R. Or g of some xy. Well, this just should be my f of x minus y squared. Absolute value squared. X minus y. For some so we have this one, and now I want to know how quickly does the L2 error converge to 0, and then I can look at, okay, how quickly does T1 and all this upper bound here converges to 0, and then I replace T by some Tn, let Tn run to 0, and look, can I show that this probability goes to 0? And we bound this probability by theorem 3.1. So exactly the form of theorem 3.1. If I assume that the functions are bounded by B, and the yi's and y are also bounded by B, so you need some assumptions here. And then you see, you get this bound here, upper bound with epsilon replaced by some t, which is Tn. So if I want to show that this probability T1 and greater than some Tn goes to 0, and if you want to show this by theorem 3.1, then it is necessary for this kind of proof that we have well, you basically need that this right-hand side goes to 0, but I ignore the expectation of the covering number. This will depend on the function space. This will be at least 1, so definitely this guy must converge to 0. So you need something like minus n times Tn squared over 128 times p squared goes to 0. And this means that n times Tn squared goes to infinity, or in other words, Tn goes to 0 slower than 1 over square root of n. So we need Tn divided by 1 over square root of n. Let's go to infinity. Because this is the same as Tn squared divided by 1 over n. So the square root of it must go to infinity, so Tn divided by 1 over square root of n goes to 0. So you can't get rate of conversion faster than 1 over square root of n for the L2 arrow. That's one of the consequences. And as you will see in chapter 4, that's not sufficient for the optimal rate of conversion. Also in view of the optimal rate of conversion will depend on the smoothness of the regression function. That will come in chapter 4. So we don't do this. Nice theorem, but not perfect for our setting. Questions? So it's an easy way to apply it, yeah? You see here? Easy. Right? And now I will present next a modification. And for this modification, I will need a modification of the theory. That will be our next theory. Okay. But before I do this, I maybe turn on, turn off. Oh, because I need this. So what's the modification? So we will use a different approach. We follow a different approach. Okay, we have the least square estimate, we look at the L2 arrow. And you can say, what can you do better here? Yeah, this is very natural composition. It's clear the function you want to estimate should minimize the L2 risk. That's how the regression function is defined, or what the special property of the regression function is. So it's natural to use an estimate for the L2 risk with an estimate, which is an expectation, so you just use a sample average. That's great. And then it's clear that somehow the difference between the expectation and the sample average will influence your error. Yeah? And how could this be smaller than, or converge to 0 faster than 1 over square root of n? Well, if you think about the central limit theorem, then if I multiply with square root of n, then I have square root of n times expectation minus sample average. Should converge to some standard normal or some normal distribution with expectation 0 and some variance. So this shouldn't go faster than 0 than 1 over square root of n. Besides, one point, if this variance goes down, then you can get things faster. And here the variance is not going down, but you can make it a little bit different. Let's do a different error decomposition. Make it T1 bar plus T2n bar. T2n bar is just the empirical L2 risk of your least squares estimate minus the empirical L2 risk of the regression function. So that's 1 over n. And T1 and bar is just the term which you need that the whole thing, that the equality holds. So that's the L2 error. Well, I make a mistake here, because the whole trick is that I make this twice. That's the main trick. That's this guy. If you look at this one, then if you just plug in, this is the what you know, this is the L2 risk of your estimate minus the L2 risk of the regression function. So you see the whole thing is the expectation of mn of x minus y squared minus m of x minus y squared. And write the whole thing as a conditional expectation, and the other thing is minus 2 times that's the guy. And now the point is that this will converge faster to 0 because faster means in comparison to above. Well, I look at again at the probability that T1 and bar is greater than T. And does this fit on this blackboard? No chance. No. No. Here. Well, this is this expectation minus 2 times this sample average, and I write it in a different form, greater than T. I add on both sides the expectation. Then I have 2 times the expectation minus 2 times the sample average is greater than T plus the expectation, and then I divide the whole thing by a factor 2. So I get, that's the same as the expectation. minus the sample average. It's greater than, I have t plus, but I have the 2 here, so I divide it by 2, then that's greater than 1/2 times t plus, and again I have the whole expectation. Yeah, here was the conditional expectation, sorry. So we need to bound this probability, and for this probability I will give the next theorem. Because next theorem, which we will apply with and before I tell you what we applied, I will write the theorem on the blackboard. And you will see. Does it fit on this page? I don't think so. No, it's too long. Questions to that point? So I'm sorry, this was a little bit quick. I made several steps at once, combined a few expectation and conditional expectations, but I think you can figure it out. It's not difficult. If you have questions, then please ask. So that next thing will be theorem 3.2. It's from Lee, Bartlett and Williamson from 1996. We are in the usual regression setting, so we have IID random variables x, y, x1, y1, and so on, which are d times r valued. That x, y, x1, y1, up to x and yn, the IID are d times r valued random variables. I assume that the absolute value of y is bounded, so also all yi are bounded almost surely. For some b greater 0, and in order to give the bound in a nicer way, I assume b greater or equal to 1. Then I assume that my functions class f is also consists of bounded functions with values minus bb. graphic class, be a class of function B. And then I have some n in n, which is my sample size. I have some alpha beta greater 0. I have some epsilon between 0 and a half. And n alpha beta greater 0. And of course, for any alpha beta greater 0 and any epsilon between 0 and a half, and I can look at the probability that there exists a function in my function space such that the algebraic of f minus the algebraic of n minus the corresponding means, sample means. Such that this is greater than epsilon times alpha plus beta plus the expectation. That's the whole probability. And then I give another bound on this guy, and it's 14 times the supremum over all points x1n, small x1n, L1 covering of f with radius beta times epsilon divided by 20b on x1n. So this L1 covering number, and then some exponential term. It's epsilon squared times 1 minus epsilon times alpha times n divided by 214 times 1 plus epsilon times e to the power 4. That's the assertion. And now if you compare our assertion with what we need here, then you see we have to say what is epsilon, what is alpha, what is beta. So epsilon we have to choose, alpha we have to choose, and beta we have to choose. And now that's your first task. Tell me what is epsilon, alpha, beta, if you want to apply this theorem to this probability. And then we will see whether this helps anything. Any idea?
Yeah, you can use alpha equals beta equals t half.
You can use alpha equals beta equals 2 half. You don't have two sums here, but you can just write t as t half plus t half. That's correct. Do this. And what's epsilon?
0 1 half.
1/2. You have 1/2 here. So you see, then I'm exactly, because now I have here, I have a random function in my probability, but I upper bound this probability that this random function has this probably by the probability that there exists any function in this function space, because my function is in the function space, that is singular holds here. Okay, and now why is this better than before? So somewhere I have written that this old thing was bad, because I've written something that I apply with some Tn equal, then I need Tn goes to 0 slower than 1/square root of n, which was bad. And why is it now better?
I mean, if we leave out constants, then we have a similar term to be lower, but not Tn squared, but Tn, so it is T divided by.
We have a similar term if we ignore, because this epsilon is just a constant, yeah, this whole thing is a constant, yeah, and this covering number, well, we had an expectation of a covering number here at the supremum, but this doesn't matter. Will turn out. So this is basically, besides that you have, we had on the other one, we had something like T in the covering number. Yeah, here we have something like T too. But now you see that here for alpha you will have T half. So if I say T equal Tn, then I need Tn times n going to infinity. That's much better. Okay, questions up to that point? Any questions? Okay, now why is this bound here better? Oh, well, we know why this bound is better, but why can we prove now a better bound? There's also one trick which I can quickly explain before we come to the wrong proof. I have to confess this would be really a long proof to prove this. But it's not really difficult. What is the big advantage which we have? The big advantage is the following. Mark. Well, we also have something like the expectation minus sample average and greater something plus the expectation. If you look at the random variable from which we take the expectation, so we let x, y, f, let x, y, f be S in theory is I think 3.2. I choose a function of f, f of calligraphic f, and the random variable where I consider the expectation minus the sample average is set. That's f of x minus y squared minus m of x minus y squared. Now I look at, any questions? Now I look at the variance of that. And you can make the following upper bound. The variance of z is of course less than the expectation of z squared. And the z squared, well, you can write this z, you can apply the third binomial formula to z. So it's an a squared minus b squared, so it's a minus b times a plus b. So you see that's expectation. The a minus b is in this time just f of x minus m of x. And I have the whole thing squared. It's f of x minus m of x squared. And the a plus b is f of x minus y plus m of x minus y, so it's f of x plus m of x minus 2y squared. So we are here. That's the third binomial formula. Now, we know in theorem 3.2, y is bounded in absolute value by b. Then, of course, the conditional expectation is bounded in absolute value by b, and the function f are bounded in absolute value by b too. So the whole thing here is bounded by triangle inequality by 4b, so the whole thing here is less equal than 16b squared, obviously, which means that the whole thing is less than 16b squared times the expectation f of f minus m of x squared. And the great point is if you look at the expectation of z, the expectation of z is just the L2 of f minus the L2 of m. That's the L2 error of f, which is just the expectation of f of x minus m of x squared. So the 16b times expectation of z. So you have this special situation that the variance is bounded by some constant times the expectation. In particular, if you're, this also indicates why you should get for least square estimated a better bound. If you have, if you want to derive some rate of conversion for least squares estimate here, then you will get some error bound for the L2 error, but then this implies as soon as we have an error bound for the L2 error, that the variance of this random variable will be small. So you could also try to use this one. First I apply theorem 3.1 to get a first error bound. Then I have a bound on the variance. And then I apply a modified version of theorem 3.1 where I bound the variance of the function to get a better bound. And a better bound and a better bound. But that's not what we will do. Instead we will use that here basically the variance is on the right hand side too. If the variance is on the right hand side too, then you have something, expectation minus sample average is greater than some t plus the variance. And then with this value you go into the Bernstein inequality and you can show that you get a better bound. That will be the trick in the proof. But you don't see it at the moment, it doesn't matter. Okay, questions so far? So this will be a property of our functions which will be used throughout the proof several times. And now we will do basically the same thing as in theorem 3.1, only much more complicated. So I will replace this guy by a sample average, in the first step by a sample average of the of a ghost sample. Then we will replace this guy by the expectation of the square of I don't see it at the moment. This is the expectation. Yes, you see that this expectation is greater equal than the expectation of the squared divided by 16b squared. So I will write here the expectation of the squared, and then I will replace this expectation of this squared by some sample average of squared. So I will get here with some squared values of these guys. Then I will use the symmetrization as before, introduce random signs. Then we will introduce some covering to get some finite set, use the union bound, and finally we will, there will be some difficulties, as you will see, to replace the expectation of the squared by the sample average of the squared, but we will handle that with another theorem, which is actually a preliminary version which you need for the proof of this one, and which you will prove then in the practicing course in 2 weeks. Basically 3 weeks, and then finally we will apply Bernstein inequality instead of having an actual. Okay, I need 5 minutes for cleaning the blackboard. We have 10:31. I will go on with 10:36. Thank you. Okay, I would like to go on, if you don't mind. Proof of theorem 3.2. In the proof I will need theorem 3.3, but I will formulate it just in the proof, not before. I use some notation. I said Z is xy. Zi is x and yi. And I said gf of xy, that's what I did before, it's f of x minus y squared minus m of x minus y squared. Then of course if I have that f is less equal than, f of x is less equal than b, y is less equal than b, and m is equal to b, so f of x is equal to b, y is less equal to b, and b of x is equal to b. Then I know that gf of xy, well, the first term is f minus y squared. That takes on values between 0 and 4b squared. The one which I subtract is also in the interval from 0 up to 4b squared. So the difference will be between minus 4b squared and plus 4b squared. And we have also just seen before that the expectation in the setting of our theorem, that the expectation of gf of xy squared is less than 16b squared times the expectation of gf of xy. And now I can just replace the assertion by and the probability is given by the probability that exists f in f, so that the first time is just the expectation of gf of z minus the sample mean of gf of zi that should be greater than epsilon times alpha plus beta plus the expectation gf of z. So see, the whole thing is much shorter. And now our proof will be divided into several steps. And I start with step 1. Where I make a symmetrization by a ghost sample. So I choose my set 1 prime until Zn prime. Such that Z, Z1 to Zn, Z1 prime to Zn prime are ID. So I make an independent copy of my Z1 to Zn. Which you can always do because this is an assertion about probability, and if I want to prove something about probability, I can change the probability space, and if I extend the probability space, I can also do it in such a way that for this probability space, there exist independent copies of my random variables. So in the first step of the proof, we will show, where is it? 3, it's here. Well, I will show that it's probability which I'm interested in. And maybe I call this probability star to save some place. And I will show that star is less equal than 8 divided by 7 times the probability that there exists f and f. And now I just replace the expectation by the average of my ghost samples. So average for ghost samples. So we have 1 over n, 1 to n. Gf of z prime minus 1 over n equal to gf of z I. And I will replace the right hand side, basically I will replace the epsilon by epsilon divided by half. And I will need n sufficiently large, and we'll see how large, sufficiently large is in the proof. Don't write it here at the moment. And maybe you have an idea how to do this. We do it in the same way as we have done it in the proof of theorem 3.1. So we fix some random function fn such that this supremum is attained. Then we start with this probability, plugging in the fn. And so we start with this probability, then this is greater or equal. We show all this time that it's greater or equal than if we plug in the fn. And then I use some Chebyshev inequality to replace this guy by this guy. And that will be. Okay, let's do it. How to do it? Choose fn. It's the fn of, which depends on my whole sample. Fn such that this expectation, so this whole thing was expectation of fn with f replaced by fn holds. And of course now I cannot make the expectation with respect to my data with my sample because this is just a integral of gf of z with respect to the distribution of x. Yeah? Otherwise, I would also integrate out these guys, which is impossible. Therefore, I write here an conditional expectation. Greater than epsilon times alpha plus beta. And offset is 1a. And it chooses f, and if such a function exists, otherwise, I choose this fn element fn arbitrary. Which means that this probability star is just the same as if I plug in here fn instead of f and forget about the existence of the f and fn. And of course, I replace the expectations by conditional expectations. And now we start with this one here, right? And lower bound it. And I need a different page, as you can see here. Then, so let's do this. This probability which I have here exists f and f. N, some I to 1 n gf of zi prime minus greater times greater than epsilon divided by 2 and alpha plus beta plus expectation gf of z. Now, because my fn is in f, of course, this probability is greater or equal than if I just replace the f by fn. Now here I have to write again a conditional expectation. Gf of z. And next I say I want to replace this first sample average by its expectation. Yeah, and then you see the difference between this guy and the other one is greater than 1/2 times the right hand side where I want to go on star, yeah. So and that's of course the case if the difference between the expectation and this guy is greater than epsilon times this guy, and the other one is greater than half. Yeah. Okay, let me write it and you will see what I mean. I write the expectation of GFN of Z given Leon minus 1 over n epsilon times alpha plus beta as expectation. And at the same time, this sample average is from same time also the expectation. Expectation of Z minus the sample average in the ghost sample. Greater than divided by 2 times alpha plus beta expectation and Z. So that's the claim here. And now maybe someone from you can explain why this claim holds. Let's do it all. But you have to show it that these two conditions here imply the conditions above. Condition above. And you're done by one tendency of the probability measure. So if this holds and this holds, then this must be. So do you see it? Yeah, you don't see it, and that's okay because it's wrong. So let me make the corrections. What do I want to make? I make all the time. Do I want to have? Yeah. I have in the theorem, I have a greater or greater equal to. I have a greater. And here I say well, let me first make a correction. We show this as a greater equal, which is basically okay, because that will be an upper bound yeah, okay, let's do it as a greater equal. Doesn't matter. And I think, oh, why do I do it as a greater equal? I think it's not necessary. But we make it as a different way here. We make it. Make it less better. Now the question is, if I make it this way, you see?
So this distance from the expectation to the sample is greater than epsilon, and
Oh yeah, and that should,
the
yeah,
other
yeah.
way,
Mhm.
which is smaller equal epsilon half. So they can't be closer than they can't have distance smaller than epsilon half.
Yeah. So the distance between the expectation and the sample average is created in epsilon times some term, and the distance between the expectation and the sample average on the ghost sample is less than epsilon half. So the difference between the two of them must be at least epsilon half. You can also see it if you use this one. This expectation is greater than this sample average plus the epsilon half time, yeah? And then I can make an upper bound by the probability by just replacing the expectation by its upper bound. Then I make a second upper bound by forget about the second condition. And then you see you have here the sample average of the ghost sample plus epsilon half times this term. So you bring this on the other side, you get this epsilon half times. So it's fine. So we are here. And now we make the same trick as last time. We say this one is the same as the expectation of the conditional probability given Z1n. Then this conditional probability is a conditional expectation of the corresponding indicator function. This indicator function is a product of two indicator functions, because both of them hold because both of them together hold if the product of the individual indicator function is 1. And then you see one of these indicator functions is measurable with respect to Z1n, so you can move it out of the conditional expectation. Then you have left the other conditional expectation, and the other conditional expectation will be just a conditional expectation of a conditional expectation of an indicator function, which will be a conditional probability. So we end up with what do we end up with? So that will be the expectation. It becomes the indicator function of the one which I move out, which is measurable with respect to Z1n, which is this guy here, yeah? Yeah, that's a conditional expectation, sorry. That's Z1 greater than epsilon times it's also this expectation of GFN. And then I have the conditional probability. And this conditional probability is the second line. Now the sample average of the ghost sample less equal than half times alpha plus beta. Expectation. That should be right. That's also a conditional probability. So we are here. So same as in the other proof, only with slightly complicated notations here. And next I want to show that this conditional probability is greater equal something, and this greater equal something will be the factor which I have here. But on the other side, so 7 divided by 8 for n greater something, and I have to argue this, and for this I have to we will consider the complementary event, and we'll show that it has a probability less equal than 1 divided by 8. And the complementary event, I will use the Chebyshev, as in the other proof. So we consider this one. And I work conditionally on Z1n, but which just means that because my random variables Z1 prime up to Zn prime are independent of Z1n, I can basically fix the value of Z1n, which means I can basically fix this function here. Yeah? So I have to consider it only for a fixed function, not for anything else. So we look now at the conditional expectation of GF of Z minus its sample averaging. And the ghost sample, what doesn't matter, ghost sample or 2 sample, greater than epsilon divided by 2 alpha plus beta plus z. That's my Chebyshev. Bounded by the variance. Well, that's the variance of z divided by, well, it's the variance of the, or it's the expectation squared of this guy divided squared of this guy, which is the variance of the sample mean, and the variance of the sample mean is 1 over n times the single variance, and the other one is epsilon half squared times alpha plus beta times expectation squared. It's this guy. We are here. So that's less than the variance of the left-hand side divided by the right-hand side squared, and the variance of the left-hand side is because it's a sample mean of IID random variables. It's a simple single variance divided by it. So we are here. And it doesn't look like you can bound it, but you can bound it because we know something about the variance. The variance, that was the trick which I made to remark after the theory, that the variance of this GF of Z is bounded by 16 b squares times the expectation of GF of Z squared. So that's 16b squared. I might copy this with n, or bind together with n, and then we have the expectation of GF of Z over epsilon squared 4 times, well, I think I want to write this one here, 4 times alpha plus beta plus expectation GF of Z. Doesn't look good because we don't know the expectation, but what I do next is I maximize this function with respect to the unknown quantity, which is the random variable. So we say this is something less than, and here I look at f of x, is the function x divided by a plus x squared. And if you look at this function, then you can look at the derivative of f. And well, now you maximize this function with respect to a. Yeah. And it turns out, well, if you compute the derivative, I use the product rule. It's 1 over a plus x squared plus x times minus 2 over a plus x to the power 3. You make the joint denominator. It's a plus x minus 2x divided by a plus x power 3, which is a minus x divided by a plus x plus 3. And then you see this has this whole thing is either greater 0 or less than 0. It's less than, it's greater 0 or x greater, for x less than a, is less than 0 for x greater a. Now you see the derivative of this function changes from plus to minus at the point x equal a, so that's greater equal than f of a. And f of a is a plus a squared. That's 1 divided by 4. Yeah. Yeah, but it's not greater equal, it's less equal than, yeah? That's what I prove. So. Does this help me? Yeah, of course. Now I can plug in here. I can forget about the expectation of x. That's 16 b squared squared naught divided by n epsilon squared 4 times 1 divided by 4. So we see the whole thing is 16b squared divided by n epsilon squared. And now I want to have that this guy is less equal than 1 divided by 8. And then you see how large 1 divided by 8, how large n must be. N must be greater than 8 times 16, 128. 128 is squared divided by epsilon squared. And we get this part. Squared over epsilon squared. And that will be actually my condition here. Which I want to prove. Questions? Please?
I'm just wondering what happened to the alpha plus beta inequality.
Excuse me, what?
What happened to the alpha plus beta inequality?
I forgot it. Very easy thing. You are perfectly alright. I have to add alpha plus beta. And the alpha plus beta will be here, yeah? Correct? So it must be also here, yeah? So it must be also here. And it should be written here too. Yes. And now you see, now I go on with the probability. Or any other questions? I have this 7 divided by 8. You have this probability, and now I have probability of I have expectation of I have basically an expectation of indicator, which is probability. So we have this first condition, expectation of GFN of Z. What was the original variables? And by definition of Fn, we have chosen Fn such that if there exists a function where this quantity is, or where this is satisfied, then it is this function, otherwise it's an arbitrary function. So it's just the same as the probability if it exists, that the whole thing, the expectation of Z minus the sample mean. Is greater than plus expectation. And that's what I wanted to ship. As far as I remember, I started, well, I cleaned it backward already, but I started with this guy without the factor 8 divided by 7. I lower bounded it all the time until I end here. And there's the 7 divided by 8 also. I lower bound with this probability, now I bring the 7 divided by 8 on the other side, and that's it. And that was the first step of the proof. And more to come. Okay, questions so far? Well, the next step will be, we are here now, yeah? I will replace this guy by the expectation of the squared of this guy. So, because the expectation of GF of Z squared is less than 16 somewhere here. Yeah, I think it's somewhere. Yeah, it was this one. The variance is less than the expectation. The expectation is less than 16b squared times this guy. Yeah. So the expectation is, on the other hand, greater or equal than 1 divided by 16b squared times the expectation of the squared. So I will lower bound the right hand side by plugging in a lower bound, so we will have a squared here, an additional constant, and then we will again replace this guy by our sample means. This will be not just a simple Chebyshev inequality. Instead, we will basically use a theorem which is of the similar kind as this one, which we will prove in the practicing course. Then you have here, you have an arithmetic mean of the GF squared of Zi and Zi prime and Zi on the right hand side. Then we will make our usually symmetrization trick, introduce random signs, split the whole thing up, condition on the Zi's, just have these random signs in here, and then finally use some covering, and then I will apply Bernstein instead of Höfting. But the big advantage will be that I will here some squares, which will be just the variance of my random variables. So the variance will be on the right hand side, and therefore with the Bernstein I will finally get a term of the then I about the probability that is greater than that is sample average minus the expectation is greater than epsilon. I will get something like e to the power minus constant times n times epsilon instead of n times epsilon squared. Okay, then I'm just finished, done for the day, and we have Monday, so I see you on stage.